Hi, so in this video I thought we'd talk about the characteristics of light, which might sound a little bit strange considering we're looking at properties of atoms, but by studying how light interacts with matter we can get information on atomic structure. So light is in the form of a wave, and waves have various properties such as wavelength, given the symbol lambda. That's a distance between two crests of two peaks, and then amplitude, which is the distance from halfway up the wave to the crest of the wave, or it could be measured from the center to the bottom, and that's the amplitude. I suppose peak to peak in that way would be twice the amplitude. And we have frequency, given the symbol mu, and that's the number of waves per unit time, which is in hertz. And hertz just means seconds to the minus one, per second. Okay, and there's another term here, another property of waves, and that is their ability to show constructive and destructive interference. So you might have seen this when in a river, say, when two boats kind of get past one another, the waves kind of extend outwards and then they interact either in a constructive fashion or destructive fashion. So when the two waves, when the crests kind of overlap, then you get a doubling of the amplitude. Or if the waves are out of phase, in other words, the crest of one wave matches up with the lower crest of the other wave, and then you get what's known as destructive interference. So destructive, you would see probably no change in amplitude, and then constructive, twice the amplitude of the original waves, as shown here. So the green and the red are two waves which are in phase, so you would add the amplitude to get the blue one, and other areas where the waves are out of phase, so the green and the red over this region here, so as the red goes up the green goes down, and so they would cancel out, so this resultant blue wave is somewhere near the middle. Okay, so that will be destructive interference. Another concept is the electromagnetic spectrum. So visible light, what we see, goes from red through the rainbow to purple, and you have a scale bar here measured in meters, that's wavelength, or frequency in hertz. You can see actually that the wavelength and the frequency kind of match. They are related, and they're related by this equation here. The speed of light is the frequency times the wavelength. So the speed of light is constant. You can look up the value of that online, and if that's a constant, then if you half, say, lambda, you've got a double mu. Yeah, so they are inversely proportional. C equals mu lambda. And you can see that here by the values. So if we take over this end, we got 10 to the minus 15 of a meter, which is very small compared with the other end, 10 to the plus 7. And then that corresponds to a high frequency, 10 to the 23 hertz, as opposed to 10 to the 2 hertz. So a low value and a high value, a high value and a low value. So they're inversely proportional, and so this is the visible spectrum which you see. So red is got a value of 700 nanometers, so that's the wavelength. So remember, 1 nanometer is 10 to the minus 9 of a meter, so that's 700, and then right through to the kind of purple region here is 400 nanometers. And all that visible region is just that small part of the spectrum here, that grey region here. So as you increase, let's see what these values are doing, 500, 450, 400. As you decrease the wavelength, and you can see these numbers are decreasing, -7, -8 through to the -50. As you decrease the wavelength, you move into this region. So ultraviolet, so kind of beyond violet. So you can't see this. After about 200 nanometers or so, that's where kind of ultraviolet kicks in. That's not part of the visible spectrum anymore. And then after UV, you get X-rays, and then gamma rays, and then cosmic radiation. And then going the other way, past red, you get microwaves. No, before you get microwaves, you get infrared. So you would have heard of infrared, no doubt, like remote controls. So that's infrared radiation. So again, that would be a higher wavelength than what we've got here. So beyond, so 750 and beyond is infrared. Keep increasing the wavelength, and then you go through to radio waves, long wave on the radio wave, so like radio 4 long wave. And where does it get that long wave name? Well, because we've got like 10 to the 3 meters here, so 10 to the 3 meters is a kilometer. So the wavelength of that radiation there is a kilometer. You know, so huge, you know, going peak to peak. And that would also have correspondingly low frequencies. Yeah, so inversely proportional. So that's electromagnetic spectrum. Probably heard of this chap here, Einstein. So he was the first to say that light doesn't just behave as waves, but it also behaves as particles. And light comes in packets or bundles, and these are called photons. And the energy of a photon is given by its frequency. So if you know the frequency, then you know the energy of these photons. E is proportional to the frequency, but there's a proportionality constant here called H, Planck's constant, which has a value of 6.626 times 10 to the minus 34 joules seconds. Because mu is measured in hertz, which is seconds to the minus 1, then in order to get energy in joules, you've got to times seconds to the minus 1 by joule seconds. So seconds cancel with seconds to the minus 1, and that gives you joules both sides. So with these equations, always check that the units work out. So that equation, E equals h mu, is very useful in determining properties of atoms, because we're going to say more about electrons later, but the atoms are in their ground states when all the electrons are kind of at the lower energy levels. Again, we'll talk about energy levels in a bit more detail shortly. But an electron can be excited to a higher energy level, a higher energy state, by receiving energy of a particular characteristic value such that E equals h mu. I mean, these energy levels have certain values, so if that value is matched by energy of a particular frequency, then the electron goes up to the excited state, and also it falls back down to the ground state, emitting energy of a characteristic frequency there. So by knowing what the frequencies are, you can get information about these different energy levels, which gives you information on atomic structure. This is made use of in various types of spectroscopy. So we have absorption spectroscopy, where energy is absorbed energy in the form of E equals h mu, so the photon energy. If that frequency matches that energy gap difference, then the electron goes up to the excited state. That would be called absorption spectroscopy. And if the energy matches the gap to fall back down from the excited state to the ground state, then the energy emitted there will be characteristic of that jump. That's called emission spectroscopy. And in these emission spectra, also known as line spectra, you get these characteristic bands. So each of these bands corresponds to a particular energy value in joules. And so with hydrogen, that's only got one electron, so the pattern you get is quite simple. So the electron can jump from its ground state to a few energy levels beyond that, but there's only one electron, so it's not gonna, there won't be too many lines in the spectrum. And in fact, the line corresponds to an electron dropping back because it's emission. So this is the emission spectrum. So the energy will go back from the excited state to a lower energy level, and you see these four lines in the hydrogen spectrum. With helium, you see more lines because now you've got two electrons, and so there will be other energy levels, so each electron can fall back to different energy levels. There's more combinations of energy levels, if you like. So helium's a little bit more complicated. By the time you get up to something like copper, the spectrum starts to get very complicated because there's lots of electrons, lots of possible energy levels, and you're going to get different lines all over the place. In fact, these lines are characteristic of the elements. So you could look at a line spectrum and say, oh, that's a line spectrum, an emission spectrum of zinc. That one's an emission spectrum of iron, say in stainless steel. So you could kind of tell the difference between two metals, for example. So the emission spectra give characteristic information about the elements involved. Okay, thanks for watching.